So today I'll be talking about how we instrumented some of our integration tests at Slack to enable us to keep tabs on potential performance regressions on our backend piece of the application. And it's a story about developing internal tools that are useful to developers, that developers actually enjoy to use, and help us not step on our toes when we're rapidly shipping code out to production. So a little bit about me. I'd like to claim that this is the moment when I started programming, but it is not. That's my dad's old machine. I think it was running MS-DOS 5 at the time. But I really only started programming completely by accident in the second half of my first year of university. Since then, I've done a short stint as a front-end engineer at a fashion startup in New York, and then eventually I made my way over to San Francisco, where I've worked in a bunch of different roles, specifically on the back-end side at Slack for 3 years now. I don't tweet very much, but you are more than welcome to follow me on Twitter and/or tweet about this talk while I'm giving it. If there's any slides that you particularly like, take pictures of them. I will definitely go through afterwards and look at everything. So that is something that I will actually do on Twitter. So in my current role at Slack, I spend a lot of my time making developers' lives simpler, more pleasant, and more productive. And that might sound a little bit cheesy, but I did pull it from official Slack branding, so you know that it's legit. But in all seriousness, a little bit more concretely, our team deals with a lot of different things. And so one of the things that we work on is upgrades to our language stack. Our backend is written entirely in Hacklang and run on top of the hip-hop VM. So these are both technologies that are open sourced out of Facebook. They made the decision to hard fork off of PHP a little bit over a year ago. And since then, they've very aggressively shipped new changes to the language. And they're iterating and shipping a new minor version almost every week now, so that keeps us very busy. We also have stewardship of our core libraries. So these are libraries that pretty much every backend engineer at Slack uses at some point when they're developing a new feature. This includes logging or metrics gathering libraries, sometimes our database access libraries. We also own all of our linting tools and our unit and integration testing frameworks. And finally, and this is the piece that I really want to cover today, and sort of in conjunction with the previous point, we have a tool that performs monitoring of potential performance regressions before they go out to production. So in order to kind of set the picture for this last piece, I want to rewind our clocks to the summer of 2017. And at the time, we were working in an increasingly growing code base where it was becoming really, really difficult to keep everything in our head. And we were trying to keep everything in our heads while we were shipping new features. And at the time, we had this nearly entirely flat directory structure. So most of our backend code was in files called lib_thing under the include subdirectory. And so there was no real reasoning about where certain ownership of files began and certain ownership ended. It was really tough to reason about where anything was. You kind of guessed, grepped around a lot. So as you can imagine, building a feature was really quite straightforward, really easy. Generally involved just a few simple steps. First, you identify any of the APIs involved, or if you needed to write a new API. You'd find all of the relevant code to modify. You'd add a few if statements, to handle the thing that you were there to handle. You'd grep around for similar code, because certainly there was someplace else this was being handled probably exactly the same way. And you'd add a few more if statements to cover that piece of the code. And then you'd ship it. Great, good job. And it wasn't incredibly sustainable, as you can probably see, given that we were also, on top of all of this, onboarding a ton of new engineers at this crazy breakneck pace. So it was a little bit like trying to launch a fast food restaurant with like a 10-page menu out of a tiny New York apartment kitchen, and then trying to increase the throughput by just throwing more chefs at the problem instead of just redesigning the kitchen. And I don't know how many of you have played Overcooked. My husband and I played through this game in just a couple days, mostly by himself, with me just falling over the edges with fully cooked meals. If you haven't played Overcooked, I highly recommend you do. It's a really great way to test your relationship without having to go to IKEA. And if you think that's it, there's more to throw into this problem. So on top of all these growing pains, right, we're deploying code to production. And every time we're deploying code to production, we're deploying it from 0 to 100% of our servers in under a minute. We had very few gates and guardrails letting us know what we were actually shipping to production. And I know there's some people in the room who actually know this number, but how many times do you think we were shipping to production in an average San Francisco workday? Any guesses? 5. Who said 100? 100. And sure, it dipped around like lunchtime when everyone was like out getting food, but then it picked right back up. So we had very little visibility into how just a single line change could impact the performance of our application. And sure, it was great because we were shipping 0 to 100 incredibly fast. So if bad things happened in production, just revert. And then that's another deploy out of 100. Who cares? Turns out large enterprise customers care a lot, surprisingly. At this time, I was working on a team that was tasked with improving Slack's backend performance specifically for those largest customers. And because a lot of our code was really difficult to reason about, it wasn't uncommon for things to get shipped every couple of one of those 100 instances, and then we had to go and fix it. And it was completely too easy to completely innocently author code, which would run out of memory on these largest teams, or just introduce a new ON linear database dependency, whatever. And it's not because we didn't test our changes. We tested a lot of our changes manually, but we'd test them out on these tiny test teams where you'd have 10 users and like a dozen channels. This is not representative of our most common Slack user, and definitely not representative of the large enterprise customers. So with many of these changes going out on a really regular basis, it felt like our team was just like treading water and firefighting all the time. And we had these visions for how the performance of the application could be so much better if we just had time to stop treading water and start swimming laps, right? So in an effort to give ourselves a little bit more of that bandwidth, we thought, OK, we need to build something which will help us identify all of these potential performance regressions before anyone's able to merge that code. So we decided to protect ourselves from ourselves. And this is a thing that a lot of programmers do. And every good programmer, knows that a good tool needs a good name. And at the time, we were naming a bunch of our tools using some combination of Slack and the purpose of the tool, right? So our PHP turned hackling linter, the Slack PHP linter, was obviously called Splinter, like Teenage Mutant Ninja Turtles. Clearly, we were building a Slack performance tool, so the only appropriate name for this tool would obviously be Slerf. From now on, I will refer to this tool as Slerf. And we made a logo for it, because a good logo means success. So we were equipped with a name and a simple goal: protect our APIs. And these are the lifeblood of the application. So if our application is unable to respond to client requests in a timely manner, Slack enters a degraded state, and our customers are definitely not happy. So it seemed like a really good place to start. We dug through our usage patterns to identify a set of APIs which are hit most often on a regular workday. And it's not a perfect metric, but it does give us a good sense of those where customers are most likely to notice a performance regression. So it seemed like a good place to start. We somewhat arbitrarily chose the top 15, partly because once we pulled the top 50, and once it reached the 16th, the usage drop-off was pretty big. Sometimes you make these sorts of arbitrary decisions, and that's OK. You're really kind of iterating on building a tool, and you'll see what works. So this is a screenshot of the top 15 APIs when we first launched the tool in October 2 years ago. And we built this little bot that runs some queries and reports which APIs are most called over the last 24 hours. And it still alerts today in Alert Slerf every Monday at 3 p.m. I can't reveal the exact numbers for business reasons. But I can give you a sense of the scale of some of these numbers. So the first one is tens of millions of times over a 24-hour period, and the 15th is millions of times over a 24-hour period. The only blurred out APIs are the private APIs that we don't publicly show to third-party developers, but the other ones you might be familiar with, and you might even see some of the blurred ones if you open up your network tab next time you're using Slack. So these APIs were used across most, if not all, of our clients, and many by third-party developers. And most dealt with either establishing a connection to Slack or reading content across different channels. And these things are absolutely critical to using Slack in general, so we wanted to make sure that they were as fast and reliable as possible. Thankfully, our hypothesis, hey, worked out. And this is a screenshot from a couple weeks ago, just to give you a sense of the different lists of the ones you can't actually see. But the top API in this case from a couple weeks ago was called twice the number of times as the top API 2 years ago. And then the bottom one is, I believe, 10x. And so it's a much tighter cluster. But mainly, this is just to satisfy curiosity. You'll probably notice that my Slack is in French. I use Slack in French. I grew up speaking French. And when we launched Slack internationally, they went internally and said, hey, if you speak another language, please switch Slack to the other language if it's one of the languages we're translating Slack to. I never switched it back because I think it's a great thing to be dogfooding your own product. And so every so often, I'll pop into a channel and I'd be like, there's a weird bug I'm experiencing here. And they're like, was this reported by a French in France customer? And I'm like, no, I work here. I'm like 3 desks away from you. OK, I digress. So we had this information, and what were we going to build? We decided to build the most low-effort MVP we could possibly conceive of, given everything that we had available to us at the time. So thankfully, we had a lot of those tools that were available to us. And we'll just take a look at a few of those. So we had continuous integration. Great, check, awesome. Every time that a commit was pushed to our GitHub Enterprise instance, it would kick off this whole flow, which read through a list of tests and ran all of those tests. We also had access to a number of QA environments, which we could deploy individual branches to for testing. And these QA environments read from our development databases. So every test team that we'd spun up to manually test some things while we pushed our code to dev branches, we could also reuse those teams in QA. And finally, while this isn't technically infrastructure, we had really verbose debug logs available to us. And this is a little bit what that looked like. So if you hit an API in Slack, and you're on a dev or a QA instance, and you have the right permissions, you can pass in an extra param, debug equals 1, and it'll tell you information about everything that the API called out to satisfy the request. And so as we can see here, it returns some information about the total time spent connecting to the database, the number of connections that it made, the total time querying the database, the number of queries that it ran, et cetera. And in this output, we cared about 2 specific metrics. So we cared about the number of database queries, and we cared about the number of Memcache queries, because we use Memcache as a distributed caching solution. And you might be thinking that relying on these 2 pieces of information is a little bit simplistic or naive. But you're thinking performance is not always tied to data fetching. What is this? It's tied to timing and all sorts of fancy performance things. But it turns out at the time that most of our serious performance problems were nearly always related to database operations of some kind or around data fetching of some kind. So for instance, we discovered that at one point, for every single unread message you had in a thread that you were subscribed to, if you went to read those messages from your threads all view, if you're familiar with that, for every single one of those messages before it loaded it, it would check that you were in the channel. You're still in the channel. Like, it's 10 messages from the same thread. Let me tell you, you're probably still in that channel. So we found all these sorts of problems, and we really wanted to make sure that we were not making these sorts of silly mistakes. But I do want to take a second to acknowledge all of the other types of data that was available to us in the debug logs that we could have used to spot regressions, specifically with regards to monitoring our data usage. So we could have looked at timings data. But that would have been actually really unreliable and unrepresentative of application behavior because our test infrastructure really wasn't that reliable at the time. So our dev databases, depending on the time of day, were under various amounts of load. And so if it was really busy handling some sort of request from some automated testing suite elsewhere, the timings data would be completely out of whack. And our QA Memcache tier had also varying availability throughout the day. So if we look at the timings, well, then we weren't really comparing apples to apples. And because this was a test that we deliberately wanted to introduce as a gate to merging code, it needed to be reliable. It needed to be something that people could trust and read the results and be like, oh, I did actually do something, and not just say, oh, Slerf's flaky again. Otherwise, we'd have a complete developer mutiny on our hands, and I personally did not want a developer mutiny on my hands. So how did this thing work? So first, we would deploy a branch to a QA environment. So based off of the commit hooks, we'd grab your latest commit, push that out to a development environment, QA environment, and then we would get all of the APIs that we wanted to test from the Slerf service. That was the 15 APIs that I mentioned earlier. And then we'd do this sort of dance. So for each of those APIs, we'd run the API against your code running on a QA environment that we identified. Then we'd run the same exact API against master QA environment, which was updated every 15 to 20 minutes. We'd record both of those runs, both of the debug outputs from those API requests. We'd record that with our service, and then we'd compare the results, and we generated a report. And unfortunately, the report wasn't super informative because we were only looking at query counts. So we only reported query counts. And it was up to the code author to figure out where they might have introduced new dependencies. And so given how much code there is to handle dnd.teaminfo, I'm not sure how long it might have taken this person to figure out exactly where they might have introduced 2 new database queries. If the change is really small, sometimes it's really obvious. If the change is a little bit bigger, then good luck to you. But it was the best we could do at the time, and it was enough to really keep the bugs, or rather the performance issues at bay. Another thing to note on this slide is the green button. So we made sure that there was some sort of middle ground. If Slerf observed a regression and blocked your PR, you could acknowledge the failure and just rerun the test suite and merge your change. It would pass, it would be fine, you could go. If you felt confident that either the results were really wrong and you let us know in channel, or you did actually fully intend to add this new database dependency, then hey, we're not going to tell you what to do. Just go and do the thing. That's fine. So we had this acknowledge flow, which was really great. And it also actually enabled us to have less friction in setting it as a blocking test to merging code to production. And it went live about mid-October of 2017. And here's a more zoomed-in view of what that looked like. And we'll see the modern version of the tool later. So overall, we definitely considered the tool a success. But there were some not-so-great bits. So we did actually catch performance regressions. Early on, Slerf alerted on various changes that would have considerably slowed a subset of production APIs, and in some cases actually probably brought down the entire application. So that was fantastic. Maggie's great. She pops into channel almost weekly to tell us that Slerf caught something of some kind. So really keeps us going. But we thought we'd avoided most of the unreliability problems around the QA environments because we weren't looking at timings and that sort of thing. But because our repo at the time was just so large, it wasn't uncommon for the deployment process of taking your branch, shipping it to a QA environment, and then unpacking it and doing everything that you needed to do to get it up and running and able to accept API requests again. That took sometimes 15 minutes to run. And so that wasn't great. And then came the extra not so great. And it's good when your CTO calls out your tool in a very public channel. So while we could work to stabilize a bunch of our testing infrastructure and decrease all the setup time, that was all doable things, there were some pretty serious limitations to how Slerf worked under the hood. And it became pretty clear about a year after we launched the testing suite, and there was a code change that was made which introduced a new database read on every single slack.com web page view, and that just kind of made it out to production, and it completely brought the application down. And then we kind of sat there and we were like, oh no, why didn't Slerf catch this? And that's because the tool issued API requests to a QA environment. It completely treated it as a black box. It had no visibility into what the application was actually doing beyond the debug output it was receiving. And that was only for APIs. It wasn't for web pages. And so we were unable to test the performance of our long-running processes, so like jobs on our job queues or indexing processes. And we were entirely unable to test web pages backed by hackline code. And that was a serious problem. So we hatched a new plan. And we went about doing that in a way that probably sounds very familiar. We built a low-effort MVP given existing infrastructure. So we sat down and we took another look at what we had, and that's when we kind of had this aha moment. Why not benchmark our integration tests? Which sounds weird when you phrase it this way. But you have to understand what makes them really powerful as a tool. And here are some of those things. So it's really easy to build up and tear down environments unique to each test. And I'll show an example a little bit more in depth of all of these next. You can also track database and Memcache usage through all of our mocking libraries that we've set up. There are no external dependencies whatsoever, so no deployment to a QA environment. And there's already a wide range of existing tests that test production behavior that's really critical to the application. So this is what a test setup looks like in some of our integration tests in our actual code. And so it creates a test team, and it creates a test user, and then you just have your test case. Our ability to tear down, to set these up and tear them down and build different types of teams, different types of channels, different types of users to exercise exactly the right kind of behavior that we want, it's really expressive. And the setup is pretty speedy and really well isolated between our different test cases. So this is something that we can leverage in order to set up all the specific benchmarking scenarios that we want to benchmark. And it's much improved over relying on these generalized development test teams that we'd set up on our development databases, which grow stale over time. And sometimes because you're testing on these dev test teams that you've set up, you purposefully break them. And that's not something that we would ever want in a blocking test. The second piece is tracking database and Memcache usage through mocking libraries. So we have these mocking libraries that kind of kick in at the network boundary of our application when we're running all these integration tests. And these libraries vary wildly in complexity. So some attempt to mimic the behavior of the external system with a really high degree of fidelity, and others accept input and just kind of give you hard-coded output back. But one of our more sophisticated libraries is SQL Fake. So it provides a near-complete in-memory simulation of MySQL. It was recently open sourced by one of my teammates, and you can check it out on GitHub. Really great tool. It was, and on the other hand, our Memcache Mock, which you can see us calling out to here, is just a key value store in memory. Like, that's what Memcache is. It's just not distributed. So because these mocks are developed by us internally, they give us an incredible amount of flexibility, and we can extend them to gather more metrics in exactly the format that we want Slerf to consume. And then another great piece is we had no external dependencies. So we did not rely on development databases or QA Memcache. It's incredibly convenient to be able to run the full suite of tests from your repo directly rather than deploying it to this environment. And if you have a local checkout of the repo at that point, you can actually run Slerf locally on your machine. And we had a wide range of existing tests. So given we already had a bunch of these, we could start benchmarking tests basically immediately once we'd made these changes to Slerf. And not all of our tests might be good candidates for benchmarking, so this is definitely one that is not, because we stub out actual behavior that is internal to the API. But there are a bunch of tests that don't stub out this behavior, and this is an example of one of those, where all it does is it calls to this API, given some test arguments, and expects a response. This is a great candidate for benchmarking. We're exercising all the critical behavior and all of its side effects. So we introduced a simple function to begin benchmarking all of these tests. And this is the actual implementation of Slerf benchmark. Basically, what it does is it takes an anonymous function and a set of options. We're not going to worry about the set of options today. But it creates a new benchmark. So that's that first line, BM. And it takes next a snapshot of all of our testing mocks before executing the code. So that's BM pre-run. Then it executes the code and saves the output of that code to a temporary variable. So that's output running the anonymous function. Then it'll take another snapshot after it's run the code that it needed to execute. Finally, it'll compute the difference between the pre-run and the post-run. That's basically just a diff of queries and query counts. And then it outputs the result of the anonymous function. And this is what it might look like embedded within an actual integration test. So we're just running the integration test for files.list with some test arguments. We happen to be benchmarking it, but really it doesn't matter within the entire scope of the test. So how does this all work together? First, we check out the code at your latest commit. We enable Slerf. Don't worry about it being bash wizard here. I've had to look this up as I was writing this, and every time I've had to modify it, I've also had to Google it, but that's OK. Google is great. Basically, all this does is it finds all the references to all the test files that have Slerf benchmark. And then for each of those, it'll run all of those test files, and in parallel, because it saves us a lot of time. Each individual test file is a test file that can be run on its own using this test wrap unit script. And then it'll repeat those steps, but for the master branch. And then finally, we run the evaluation script. So as we are evaluating each of these benchmarks, we're outputting JSON files to disk on the CI box that's running all of this. And so we take all of those output files, we match them up by ID from your branch running this specific benchmark and master running a specific benchmark. We'll do the comparison there. And in these comparisons, we're actually able to collect much richer information about what operations were going on under the hood. We saved all this stuff into those JSON files, and it gives us much, much more informative results in the UI afterwards. And so once we've collected all that information and we've created this evaluation, we report the results. And so this is what the new version of Slerf looks like. We have a whole bunch of new categories. So we not only look at regressions, we looked at different tests that were acknowledged. So if you did intend to actually make that change and you acknowledged it, then we keep track of that. Any improvements, which are great. If you removed any tests, so if you removed a benchmark just because it wasn't doing what you wanted it to do, that's fine, but we also require you acknowledge that. If you added benchmarks, great, we love you. No status, something went wrong with the evaluation, and no change, everything is totally the same between your branch and master. Good job. We also now are able to show you the full queries that we think might have been added, the APIs that we think might have been impacted, and a complete call stack where we think that new query is happening, which is so much better from a developer perspective. When you're being told Slerf is failing, oh no, you can actually find where it thinks these new queries are happening. And if you do actually ship an improvement, we give you confetti. So let's cover the good, the bad, and the not ugly of this new setup. So we were able to catch performance regressions with this new setup as well. It's much, much faster. And it's now easier than ever to add these benchmarks. We're not relying on these 15 top called APIs anymore. The alert still goes off because it's interesting to see these usage patterns. But now people can just benchmark anything that they think is relevant. And now we're benchmarking nearly 800 different code paths in comparison to the 15 prior. So it's a much safer world to be in. Unfortunately, with any testing suite, the more you add tests, you slow the whole thing down. So while Slerf is not the longest running test that is blocking merges to production currently, it's getting up there. So that'll be definitely something that we have to address in the future. And instead of the ugly, I'll talk about the amazing. So because our mocks make Slerf completely extensible, we're looking to introduce different metrics around memory usage, where we can pre-run record the amount of memory that's used, post-run record the amount of memory that's used, easily subtract the amount of memory that we're using for our in-memory mocks, and report that finding. We can also look at the number of rows returned. Because SQL fake is basically an in-memory SQL implementation, we can actually trust those numbers. and timings data. So because we have no network dependencies in our integration tests, the timings data is actually somewhat reliable. It might not look like production, but running the same exact tests in the same exact way between your branch and master should return reliable results. So, some takeaways. If there's anything you should take away from our experience with Slerf, apart from great names and logos make things great, you should learn to build from what you have. Take inventory of the tools you have available to you, and you might be surprised to see the different creative ways that you can combine them. You might not get an optimal solution, but you might be able to get a surprisingly effective approximation. And if it is an approximation, that's when you have to gate responsibly. And what I mean by this is that if you're planning to introduce a new test that's able to block merges, you have to think really carefully about what you want that interaction to look like for developers on the other side. So we were able to make Slerf a blocking test because we had a way for developers to acknowledge all these failures and move on. We trusted them to make the right call, and that's really paid off for us. And I just want to thank all these wonderful people who worked on Slerf with me. They're not here, but they might watch this on YouTube at some point, and they were great. I also brought Slerf stickers with me, and they're at the Slack table outside. Sure, it's the old logo. Who cares? It's got a Smurf hat on it. It's cute. It's an internal tool, branding, whatever. Thank you.